Hello everyone, my name is Nathalie Naddeh, and today I'm going to present to you the scope of our paper, which is entitled A Large Deviation Model for Latency Outage for URLLC. So, as we know, ultra-reliable and low-latency communication services are introduced in the 5G new radio to be able to respond to the demands of the critical services such as autonomous driving, mission-critical applications, etc. And that will help reach low latency such as 1 millisecond and high reliability of 10 to the minus 5. So 3GPP introduced several techniques to reach this low latency. For example, we can name preemption, we can name short transmission, different numerologies, etc. And these techniques, they enable latency reduction for radio level, but these techniques assume that the resources are always available and the latency is only due, for example, to packet alignment, scheduling grant reception, or packet decoding. So when the resources are insufficient or the traffic load is very high, we need an additional component to the radio level, which is the queuing delay, to be able to meet the latency of the URLLC. So if these URLLC services are in competition between each other, preemption is not possible in this case, and we cannot avoid queuing. So in this case, an over-reservation or a reservation of resource blocks are needed to respond to this high traffic intensity. So in this paper, what we aim to do is to develop a mathematical model for computing an outage probability of the URLLC service based on large deviation bounds. We needed to propose two cases with and without queuing delays with the application of several deviation bounds to give the optimal resource allocation for the URLLC services. And then eventually we evaluated the performance of the proposed bounds when compared to system simulations. So in our system, we consider a 5G cell with static URLLC services users. We have an STI of T millisecond. We have RBs for a URLLC, and the traffic of URLLC is considered sporadic. Each packet has its own modulation and coding scheme, which gives us the spectral efficiency, and it has a p bits of size. So to calculate the number of physical resource blocks for each packet at a time t, equation A gives us the formulation of the number of resource blocks. So we need to see the global requested number of RBs by packets at a time t to be able to reach the low probability outage. Here we name xu of t as a random variable that is the requested number of RBs per user at a time t. So 0 if with the probability 1 minus q, and Ri with the probability q times pi. And the total number of RBs is given by equation 3. And the objective is to keep the outage probability below a value epsilon, which is, so the total number of requested RBs should be below, of the total number of RBs that are greater than a given reserved resource block R should be lower than epsilon. So this problem, the equation 4, is solved using large deviation techniques in our case by calculating the upper bounds. So here we consider the outage bounds with tight delay budget with no waiting, and we calculate the mean and the standard deviation of xu and R as in equation 5, 6. So we define a variable that is the xu minus the mean of this random variable, and we rewrite the equation 4 as follows. And then we define another variable t that is r minus the mean over the deviation, and we rewrite the equation 4 as an equation 8. And this equation is solved using several bounds in our case, by the Chebyshev, Bernstein, and Banach bound. And the mathematical calculation in this case for each bound is detailed in the appendix, since it is very detailed calculation. So before we considered the model with no weighting, and now we are considered with a looser constraint, which is a packet can stay for longer than delta 1 equals 1 slot. And in our case, we wanted to reach a target of 1 millisecond of queuing delay. So we set the delta to 7 slots. Here at a given slot 0, the amount of RBs that will be needed in the future to serve all the packets that arrived in the backlogged traffic is equals to B0, where the amount here acts as the amount of resources that are needed at time 0. B1 is the backlogged, the overflow traffic from the previous slot, and R is the available resource. So recursively, we can also compute B minus J as follows. And the outage probability is computed for the new packet that has to wait more than delta slots as equation 11. So here, apart from the delta slots that can be in the queuing delay, we consider also a system with a memory of M slots and neglect all the packets that arrive that are backlogged before the M slots. So we rewrite the equation of probability as follows, including delta, M, and the backlogged traffic. And here we suppose that the system is not overload for a very large time, and as we can see, figure 2 shows that the memory of 10 slot gives us a good approximation of the system, since after 10 it becomes very stable. And by removing the factor, the maximum factor, we can rewrite the delay the probability as this equation 13, and this equation also, as in the case of non-queuing, is solved via the same upper bounds. So to be able to use this in the real world, we created a simulator that gets as an input the MCS of the users, the average number of packets, and the MCS distribution, for example, of a cell. And it gets the packet that are generated following Bernoulli's law, following this MCS distribution, since they choose the MCS following this distribution. For the scheduler, the packets are queued as first come, first served, and if the packet is not totally scheduled on slot T, it can remain in the queue, and it can be scheduled on 2 consecutive slots. And eventually this simulator gives us an output, the outage probability that should be lower than epsilon. Here we give two different numerical application of this analytical bound to see if these bounds are applicable in the real network. We illustrate here the outage probability obtained by analytical bounds and the system simulation that we already did with no weighting. And we can see here that the Banach bound, which is Banach bound 2, detailed in the appendix, is the closest to the system simulation with a dimensioning, with an optimal dimensioning mode. And for the queuing case, we can see here, for example, that the Banach bound 2 is also very close, and it's closer basically to the system simulation. Here, what we did also, we compared our system simulation to the state-of-the-art work, which includes a queuing model of MMCK model. And we see here we applied it on two cases. One gives an average MCS, and one is 90% percentile, which is the worst case, as we can see that the users are on the edge of the cell. Here we can see that the percentile, the 90% percentile, is very off the system simulation, but unfortunately, as we see that the average MCS gives good result, but in some cases, for example, here it underestimates the number of resources that we need. So in this case, we can't use the average MCS in the next steps. So this simulator was a one cell simulator, and now we wanted to test it on a large system level simulator. We take, for example, the NSSMF, which is the Network Slice Subnet Management Framework that englobes, for example, the MCS, the distribution estimation model that gets from the cells that the MCS distribution. It gives it to the resource dimensioning model, which gives us the system simulation, getting as input the QoS and the traffic prediction, and gives us as an output the resource reservation per slice, the optimal resource reservation per slice, given by Monte Carlo simulations, back to the scheduler. So to give this simulation some parameters, we applied this simulation on 13 G-node Bs with a subcarrier spacing, for example, 15 kilohertz, number of RBs 106, TTI size of 0.1443, and the traffic, as we said before, is Bernoulli. And we can see here we perform several simulations with different arrival rates, as we can see for the packets. And we saw the required reservation based on the arrival rate. We saw that the MMCK percentile, 90 percentile, is, as we saw before, is very needs more of a reservation than the Bennett bound, here the analytical bound. And we can see that the analytical bound gives us a good reservation when compared to the system simulation that is given by the resource dimensioning model, and which gives us an over dimensioning of around 15%. That which is not a bad over dimension, not a bad over reservation cost for an applied analytical model. So in this paper, to conclude, we developed a framework for URLLC traffic that combines analytical model with measurements of radio conditions, as known as the MCS distribution. Based on the dimensioning of large deviation bounds, we get the optimal resource allocation for the URLLC. And then we compared the analytical model with a numerical simulation in a new queuing and non-queuing delay, and derived the outage probability bound of the two cases. We tested it on large-scale system, and we showed that the URLLC targets are achieved with an acceptable over-dimensioning cost. Thank you. If anybody had a question.